Find the derivative f prime of x with respect to the variable x is the function note the symbolism. When we talk about a derivative, one way to represent it is with this little prime. This is called f prime of x. And this is the way we will distinguish a derivative of a function. So the derivative of a function, f, with respect to the variable x, is the function f prime of x, whose value at x is hopefully you're thinking, what? I know that. It's all I've been doing here for the past few weeks. And you have. The instantaneous rate of change of a function can also be called the derivative of the function. You got to get that. A derivative is nothing more than the slope of a curve. The slope of a line tangent to a curve, the instantaneous rate of change of a function. So now we just add derivative to that. So you already know this, so we're already ahead of the game, okay? We already know this. Now, the domain of a derivative is a set of all points in the domain for which the function f, the limit will exist. And if f prime of f exists, we say that the function has a derivative at x. The function that is differentiable at every point in its domain is said to be a differentiable function. So we will talk about being differentiable at a point, and we will talk about a function being differentiable. In order for the function to be differentiable, it's got to be the derivative has to exist at every point in the domain of that function. So of course, one of the main things that we're going to do in our first lesson is we're now going to ask you to find the derivative of a function, which you now know is we're just asking you to find the slope of the curve. We're asking you to find the slope of a line tangent to the curve. We're asking you to find the instantaneous rate of that function. We're asking you to find the derivative of, as h approaches 0, of f of x plus h minus f of x all over h. So we're going to take the limit as h approaches 0 of x plus h quantity squared minus f of x, which is the function x squared, all over h, which gives me the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h, which gives us the limit as h approaches 0 of 2xh plus h squared over h, which gives me the limit as h approaches 0 of 2x plus h and we find that our limit is equal to 2x. Now, if I wanted to know what the derivative of the function was at a particular point, we would have to give you the value of x. And you would simply substitute that value of x in. And so at any point on the curve, I can find the slope at that point by substituting that value for x in. So like I said, this is just all review. You've been doing this for quite some time now. but now we call it finding the derivative of a function. Finding the derivative of a function. We do have an alternate definition of a derivative, and this is for finding the derivative at that particular point. But if you want to do it all in one swoop, we've got our alternate. Derivative at a point. The derivative of the function at the point where x is equal to a is, so I want to know what the derivative of the function is at a particular point that we call a. Here we take the limit as x approaches that value a of f of x minus f of a all over x minus a. This is known as the alternate definition for the derivative of a function at a point. So if I ask you, what is the derivative of a certain function at a point, I can use the first definition and then evaluate, or I can use the alternate definition and come up with the derivative at that point. For instance, let us find the derivative given the function find the derivative of f of x equals 1 over x at x equal 2. Using the alternate definition, f prime of 2 is going to be equal to the limit. And a lot of people screw this one up because you know what they do? They take the limit as x approaches 0. We've been always allowing everything to approach 0 for the longest time that we forget that x can approach any real number that we choose. In the alternate definition of the derivative, x has always got to approach the value of x. So the limit as as x approaches 2 of f of x minus f of 2 all over x minus 2. So I've got the limit as x approaches 2. Well, f of x is the expression 1 over x. F of 2, of course, would be simply a 1/2. So I've got 1 over x minus a half all over x minus 2. Back to the very beginning, anytime I want to find a limit, I always try direct substitution. Of course, it fails in this problem, so I need to manipulate a little bit. And we have already taught you, anytime you've got sums and differences of rational numbers in numerator or denominator, doesn't matter, you got to combine them together first. So I've got 2 minus x all over 2x all over x minus 2, which is the limit as x approaches 2 of 2 minus x. Now let's try this. Negative 1 of x minus 2 all over 2x times 1 over x minus 2. I saw my denominator was x minus 2, my numerator is 2 minus x. I know that they're opposites of one another, and I'm sure that they're going to cancel out. So I went ahead and factored a negative 1 out of this numerator to get x minus 2. So now clearly these two factors will factor out, leaving me with the limit as x approaches 2 of a -1 all over 2x. Now I can use direct substitution, and I can find that my derivative, of course, is equal to a -1/4. Easy peasy. If you did not use the alternate definition, in other words, if we gave you the function 1 over x, we would find that the derivative with respect to the variable x, if I worked it out using the original definition, I get -1 over x squared for the derivative. I just skipped all the work, okay? And f prime of 2 still gives me that -1/4. So you've got a choice to make now. You've got an option when we're trying to find the derivative of a function at a point. You can use the original definition, find the derivative of the curve, find the slope of the curve, and then evaluate it. Or you can use the alternate definition that takes you directly to that particular point and what your derivative is equal to. The notation that we use with respect to derivatives. Well, I've already shared one of them with you. The most popular, well, I don't know if I'd call that, it's one of the most popular symbolisms that we use for notation. Of a derivative. Read f prime of x. That's one way to represent a derivative. Sometimes we just write y prime. And again, I've got to have that prime mark. Another way to represent a derivative, and I would say this is the one that is used most often. It is read dy dx, dy dx, not dy divided by dx. It's not a quotient, it's not a ratio, it's simply dy dx. And what it means is the derivative of y with respect to the variable x. That's what that says. The derivative of y with respect to the variable x. df dx. Believe it or not, I've never seen this one before, but it is one that works, but you'll probably not see it either, not in our textbook. df dx simply reads, again, the derivative of f with respect to the variable x, the derivative of f with respect to x, and d dx represents derivative, so that one simply says the derivative of f of x, the derivative of f of x. And those are the different symbolisms that we can use to represent or to identify a derivative. And like I said, these two here probably are the most common that you will see as you study the example problems out of your textbook or anywhere else that you are studying and looking and learning about the calculus. In our definition, we said that the derivative of a function is a function, okay? So one of the things that the College Board really, really, really likes, that is really, really, really difficult, is looking at the relationship between the graph of a function and the graph of its derivative. The graph of a function and the graph of its derivatives. Because we can think of the derivative at a point in a graphical terms as slope, we can get a good idea of what the graph of a function f prime looks like by estimating the slopes at various points along the graph of the function f. We estimate the slope of the graph of the function f in y units per x units at frequent intervals. We then plot the estimates in a coordinate plane with the horizontal axis in the x-axis and the vertical axis in the slope axis. Now, to put that all together, they've got a nice example problem in the book that I don't even want to put on the board, but I do want to draw your attention to it. It is on page 101 of your textbook. Page 101 of your book. Example number 3, page 101. Example number 3, graphing f prime from f. Given the graph of a function f, we want to draw the graph of its derivative. So, graph the derivative of the function f, whose graph is shown in the figure. Discuss the behavior of the function in terms of the signs and values of f prime. So there on the left-hand side, that left graph, you can see is your function. They've got it all labeled nicely for you, and they've picked different points at A, B, C, D, E, and F. And all we did was, at these particular points, derivative is slope. Always remember that. So at point A of function f, we guesstimate, and I emphasize the word guesstimate, what the slope of a line tangent to the curve at point A would be equal to. And as you can see there in their little diagram, they say that the slope at point A is equal to 4. Because they went up 4 units to the right 1, so they say that a line tangent at point A would have a slope of 4. And that's just a guesstimate. So what do we do with that information? So if the slope is equal to 4, then in the graph of the derivative, which is there to the right, we are at the point 0, 4, where the y-coordinate, your range values, are the slopes that you found by looking at the graph of f. And then we go to point B, which is at 1, B, and we find that that slope is approximately equal to 1, up 1 over 1, 45-degree line, if you will. So at x equal 1, in the graph of the derivative, you'll note that we plotted the point 1, 1. And then at point C, that's where a horizontal tangent line would be. What's the slope of a horizontal tangent line? It's 0. So at 2, 0, they plot point C, and then point D, point E, point F, and then they come up with the curve of the derivative from the graph of the function f. Not one of the easiest things to do, but hopefully we will provide for you enough practice that you can do it. The thing that you need to be aware of in the comparison of f to f prime. First of all, I got to make sure, I guess, if I gave you the graph of f, and I said the graph looks like this, would you tell me that this graph is increasing or decreasing? What do you think?
Decreasing.
Increasing? Because as we allow x to get larger, what is the y values doing? They are getting larger. Therefore, we say that this is a graph that is increasing. Whereas if I have a graph that looks like this, that graph is decreasing, okay? That's what I want to look at in graph F, there in that example. You can see that from point x equals 0 to x equal 2, the graph is increasing. But look at the graph of the derivative in that same interval from 0 to 2. What is it doing? Or what, not what is it doing, what is it? Yeah, it's decreasing, but I don't want to know that. I just want to know that it is positive or negative.
Negative.
If you have a graph above the x-axis, is it positive or negative? It's positive. So, please note, if your function f is increasing, then f prime has got to be positive. Critical. Extremely important. And what do we mean by f prime is positive? All we are saying is that f prime has to lie above the x-axis. From x equal 2 to x equals 6. Look at function f. It's now decreasing, right? It's going down. But look at the derivative from 2 to 6. Does the derivative lie above or below the x-axis? Clearly it's below. So we need to establish the fact if f is decreasing, then f prime got to be negative. That is, f prime is below your x-axis. And the third thing that we want to point out if x has a horizontal tangent, and of course if you look back at the graph at x equal to point C, we've got a horizontal tangent line. What does that translate into the derivative? Well, at point C, it's going to be a y-intercept. It's going to be a y-intercept. So when f has a horizontal tangent, then f prime is 0. And it doesn't matter how simple a given function is or how difficult a given function is. The relationship between the function and its derivative will always be true. If function f is increasing, then the graph of your derivative in that area, in that domain, will lie above the x-axis. If function f is decreasing, then the graph of the derivative will lie below the x-axis for that domain or for that interval. Wherever function f has a horizontal tangent line, the graph of your derivative will pass through the x-axis. The graph of your derivative will be equal to 0. So some good study material here in this lesson that I'm going to ask you to look at. The other type of problem in terms of graphing that they get into deals with putting together a scatter plot and trying to come up with a regression curve that would fit that scatter plot. Regression lines, as I've told you before, even though I made you do some in here, regressions are not covered on the AB curriculum, so we won't even worry about that. So in example number 5, you don't need to worry about example 5 as you study the book, okay? It's called graphing the derivative from a given set of data. And then finally, just like with limits, derivatives have a left-sided derivative and a right-sided derivative. One-sided derivatives. A function y equal f of x is said to be differentiable on a closed interval from A to B if it has a derivative at every interior point on the interval. That makes sense to me. If a function is differentiable on a closed interval, then every point on the interior has to be differentiable. And if the limits, the limit as h approaches 0 from the right of f of a plus h minus f of a and that's the way we distinguish our right-sided limit. And the limit as h approaches 0 from the left of f of b plus h minus f of b all over h. Left-sided limit. If these two limits exist at the endpoints, so a function y equal f of x is said to be differentiable on a closed interval a to b if it has a derivative at every interior point on the interval, and if the limits, which we call the right-sided limit and the left-sided limit, exist at the endpoints. Then and only then can we say that the function is differentiable on the closed interval. So I got to prove that the function is differentiable at every point between a and b, and then I got to prove that the derivative at a and the derivative at b, the left endpoint and the right endpoint, also exist. If I can do that, then I can say that the function is differentiable on the closed interval. The usual relationship between one-sided limits and two-sided limits. Now hear that? Limits. I'm not talking about derivatives right now. what we have established with the usual relationship between one-sided limits and two-sided limits, meaning that a limit will exist if and only if you come in from the left-hand side and the right-hand side. If the two limits are the same, then the limit exists, right? Same thing's true for derivatives. If you come in from the left-hand side and find the derivative, if you come in from the right-hand side to a point and find the derivative, if the left and right-hand limits are the same for the derivative, then we say that the function is differentiable at that point. The derivative exists at that point, just like the limit exists at that point if the left and right side limits are the same. So again, something that we already know. Thus we say a function has a derivative at a point if and only if the function's right-hand and left-hand derivatives are defined and are equal at that point. So a typical problem that you probably most assuredly will come across. I want to show that the following functions has right and left derivatives at x equals 0, but no derivative exists at x equals 0. And of course my function is going to be a piecewise function. The only way that I can show that a derivative exists at a point is to show that the left-sided derivative and the right-sided derivative exist, but more importantly, they're equal to each other. How do I find a derivative of a function? Well, I have to use the definition of a derivative. So for the left side, I'm going to take the limit as h approaches 0 from the left of, well, coming in from the left, I got to use this function. So I've got negative 0 plus h minus 0 all over h. The limit as h approaches 0, what do I have? Negative h over h, which is equal to a negative 1. The derivative, as I come in from the left-hand side of this function, is equal to a negative 1. Got to do the other side. So now I'm going to take the limit as h approaches 0 from the right-hand side, so I got to go to the second piece here, which is going to give me 0 plus h minus 0 all over h. Limit as h approaches 0 from the right of h over h equals 1. I showed again that the right-sided limit does exist, but the question is, does the limit at x equals 0? Or does the derivative exist at x equals 0? Is the left and right-hand side the same? No, of course not. Derivatives are not equal. At x equals 0, the function does not not have a derivative at 0. So a few things. Yes, sir.
Why didn't you substitute the 0 back in
Why didn't I substitute the 0 back into what?
to the limits?
Well, what is the limit of a constant? It's just that constant, right? So when I rename this as a -1, I'm looking at the limit as h approaches 0 of -1. I kind of skipped that step. So the limit's got to be 1, because the limit of any constant is that constant. And same thing happened here. This is really 1, so the limit as h approaches 0 of 1 is 1. There's no h to plug into. They canceled. So most importantly, please, 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 please remember that a derivative is nothing more than the slope of a curve. More importantly, a derivative is nothing more than the instantaneous rate of change. Because on the AP exam, what they're going to do is they're going to ask you to find the instantaneous rate of change. And you've got to realize, oh, they're just asking me to find the derivative of this function. And if you get that connection now, it's going to be much, much better for you when it comes exam time. Please remember the definition of a derivative, where you take the limit as h approaches 0 of f of x plus h minus f of x all over h. Please remember that the relationship between the graph of f and f prime is extremely important. If f is increasing, then f prime is positive. If the function is decreasing, then f prime is negative. And if the function has a horizontal tangent line, then f prime is equal to 0. That's the highlight of this lesson. Now we've thrown in some other things to kind of try to reinforce what these particular things say. But that's what you got to get. So for tomorrow,